Hello everyone, welcome to the next topic of computer architecture and organization. So in this class we are going to discuss a very important and very, you can say, a very conceptual topic, that is pipelining. And in this chapter we will see lots of things. So first we will see the basics of pipelining, and then we will move forward and we'll go to the most popular pipelining, that is RISC pipelining, reduced instruction set pipelining. That is the most widely used in the systems, and our modern systems are also based on RISC. And there are many processors like MIPS which uses the RISC pipelining. So our main concentration will be on studying about the RISC pipelining. And then we will see what are the problems that may occur in the pipelining. That means what are the issues that can degrade the performance of pipelining. For example, there may be some problems which can be categorized in structural hazard, data hazards, and control hazards. We will talk about these hazards, and we will see in what kind of hazards the stall cycles are possible. Stall cycles are nothing but simply waiting cycles. Waiting cycles are dangerous for pipelining because they will increase the CPI of the pipelining. CPI means cycles per instruction. Normally the CPI of pipelining is 1, that we will see why. And due to the stalls, the CPI of pipelining may increase. So we will see what is structural hazard and what are the solutions of these hazards. We will see what is data hazard and what is read after write, what is write after write, and what is write after read hazards, and what are the data dependencies like anti-dependency, output dependency, and true dependency. And we will see how we can overcome these problems. And then we will see what is control hazard, and control hazards are normally occur due to the branch instructions. And we will see how we can fill the pipelining so that there will not be stall cycles. We will see some solutions to the control hazards like delayed slot or branch prediction. So we will see all these things, right? And in the end we will see what is data forwarding and how it is being done in the pipelining. Then in the end, the most important part is solving the questions on pipelining. So this topic is completely based on practice. So does not matter if you understand the complete concepts of pipelining. If you do not correctly solve the previous year question, then maybe there will be some issues in the real examination, because pipelining questions looks very easy, but they are not that easy as they looks. Okay, so we'll see very simple questions, and then we will see very complex questions in pipelining that can be asked. 70% of the questions in the last 20 years are very easy, that is directly formula based, but 30% questions are little bit you can say tricky, in which a crooked mind is required, right? So let us start and see what is the pipelining and how we are taking the advantage of many components of the computer system to execute the instruction in a pipelined manner so that the throughput of the CPU increases, right? So when we talk about pipelining is simply like your assembly line in any manufacturing plant. Most of the books will give you the example of the manufacturing plant in which the car or bike or any other you can say part is being developed in the simple you can say pipeline. So you know that if you go to any plant of the car, then you will see that there will be multiple lines which is called as assembly line. So in the first line you will see that they will be manufacturing the body of the car, then they will send it to the next unit, and the next unit will simply put the tires and everything on this car, and then next in the next unit they will put the interior of the car, and then they will paint the car, and then they will test it. So like this there will be multiple units which will be performing this particular task, right? So what we can do is, when we know that when we are, let us say, in the first 1 hour we are building the body of the car, and in the next hour we are building the tires and everything of the car. So after the first hour this particular person will be free, so we can give it a second task. In the same way, in the pipelining also we are doing the same thing. What we are doing is, we know that the instruction executes in stages, and the stages are instruction fetch, then instruction decode, and then execute and memory access and write back, right? And all these things are done on the different components. For example, when we talk about instruction fetch, we will fetch the instruction from the memory. That means in this particular cycle we are using the main memory. And then we will talk about instruction decode. In this particular stage we are decoding the instruction. For that we are using the decoder, right? Or we can say control unit. Then in the next stage we will see that we will fetch the operands. So it is possible that operands are in the memory, so in this case we will also have to access the main memory. Then you will execute the instructions which are ALU or load store instructions or some branch instructions. So ALU will be used in this particular stage, and then write back may be in the registers or it may be in memory. So in this stage register or memory may be used. So we know that different tasks of the instruction are being performed on different units. So what we can do is we can pipeline these units so that we get the better throughputs from the system. So pipelining is an implementation technique whereby multiple instructions are overlapped in the execution. It takes the advantage of parallelism that exists among the action needed to execute the instruction. So they are different components, so they may work in parallel, right? And that is the concept we are going to use in the pipelining. What we are doing is in the pipelining we are saying that we will keep accepting the input on the one end until before the output of the first task is on the output line. So if we talk about the non-overlapping execution, or we can say sequential execution. So you know that the sequential execution of the instructions will be something like this. For example, let us say we have a processor which allows only the sequential execution of the instructions. Sequential execution of the instruction simply means that the next instruction will be fetched only when the last instruction is being completed. For example, first instruction starts, so this instruction will fetch the instruction, then we will decode this instruction, and then we will perform the operation, or we can say we will execute this instruction, and then we will write back the result, right? So let us say this is the first instruction. So in the 4 cycles we are executing one instruction, right? Then the next instruction will be fetched only after the write back stage of the last instruction. That is, we will fetch the next instruction, then we will decode it, and then we will do the execution of the instruction and then write back. So after the write back of the this previous instruction completes, so I2 will take 4 cycles, right? What is the meaning of cycle? We will see this. Then the next instruction will be fetched. So like this we will keep going. So you will see that if we have 2 instructions and each instruction takes 4 cycles, so 2 instruction will take 8 cycles. That means if we talk about the execution time in case of non-pipelining, it will be simply the number of tasks into the time taken to execute one task in non-pipelining, right? So for example, let us say the time taken to execute one task in case of non-pipelining is, let us say, 40 nanoseconds. Let's say each of the stage takes 10 nanoseconds. So let us say 10 nanoseconds is taken by each of the stage. So in this case it will take, if we let us say we are executing 5 tasks, then it will take execution time in non-pipelining system will be, so 4 instruction into 40 nanosecond are taken by one instruction, that will be 160 nanoseconds, right? 40 nanosecond by first instruction, then 40 nanosecond by second instruction, like this, and so on. And you will see that if we do this in the pipelining manner, what we can do is we can overlap the stages of the pipelining. That means when we are decoding one instruction, the another instruction can start fetching. So that means if we talk about the pipelined execution, in case of pipeline execution, what we can do is, so this is called as space-time diagram that we will be using throughout this lecture. So let us say we have the instruction I1, and in the first cycle we are fetching this instruction, and in the second cycle we are decoding this instruction, and then let us say we are executing and then writing back the result. So let us say this is the cycle 1, 2, 3 and 4. So CPU, all the stages of the pipeline will be connected to a common clock, and the frequency of the clock will depend on the maximum time taken by a stage. So it is possible that the different stages of the pipeline are taking a different time. So it makes sense that to set the clock to the maximum cycle time. So for example, let us say if instructions fetch takes 10 nanoseconds and instruction decode takes 20 nanoseconds, execution takes 15 nanoseconds, and write back takes 10 nanoseconds. So the maximum of this is 20 nanosecond. That means the clock connected to all these stages will be having the frequency of 1 upon 20 nanoseconds, right? So that will be the frequency in gigahertz, or you can say 0.050 gigahertz, or you can say 50 megahertz. That will be the frequency of the clock. So clock frequency will be set according to the maximum, or you can say slowest unit of the pipelining. So this is the slowest unit of the pipeline. According to this we will set the clock, right? So we know that in the first cycle we are fetching the instruction I1. In the second cycle we are decoding the instruction. So what we can do is, because in the second cycle the instruction fetch unit is free, right? We are not doing any operation on the memory, we are decoding the instruction I1. So what we can do is, in parallel we can start fetching the instruction I2, right? And because in the third cycle we are executing the instruction I1, what we can do is we can start decoding the instruction I2, because in the third cycle the decoding unit will be free, right? So in the third cycle you will see that the fetch unit is also free, so we can start fetching the next instruction like this. So in this fourth cycle we can start executing this instruction, because in the third cycle the instruction I1 is finished the execution, so I2 can start the execution, right? And then I3 can start decoding it in this unit, and then we can do the execution of this instruction, and in the parallel we can start fetching the instruction number I4. So like this we will keep going. So given that none of the instructions are dependent on each other, so pipelining is that simple, but in some cases we will be having some issues. But the main idea is that in the pipelining we can start accepting the new instructions on one end when the other instructions are already in the execution, right? So for example, let us say we have a pipelining system in which we have 5 stages. Let us say there is a processor which executes the instruction in 5 stages. Let us take stage 1. So every instruction will go through these stages to complete the execution. Stage 3 and stage 4 and stage 5. Let us say there are 5 stages. So these are the cycle numbers. So we are assuming that every stage will be completed in one cycle. Okay, every stage will be completed in one cycle. So what will be the cycle time of the pipelining? That will depend on the maximum, or you can say the slowest unit of the pipelining that we already discussed. So this is your instruction I1. Let us say then we have the instruction I2, and that starts the fetching, or you can say stage 1 in the second cycle, and stage 2 in the third cycle, stage 3 in the fourth cycle, and stage 4 in the fifth cycle, then stage 5 in the sixth cycle, right? And let us say we have the third instruction which is also like this. So remember that you cannot write S1 above S1, because in the same cycle we cannot perform 2 tasks on the same unit. In the same cycle we cannot perform 2 tasks on the same unit. For example, we cannot perform the instruction fetch of the I1 and I2 at the same cycle, right? So that's why this diagram looks something like this. So then you will see that the next instruction will be executed will be completed in the 7th cycle, right? So let's say you have the 4th instruction, then that instruction will be executed that will finish the execution in the 8th cycle, right? So from this you can see that if we have n instructions, okay, if we have the n instruction, the first instruction will take k cycles, right? The first instruction will take k cycles. So you can see that the instruction I1 will take 1 2 3 4 5. We have 5 stages, so first instruction is completed in the 5 cycles. Or you can say if we have k stages, the first instruction will take k cycles, right? And the remaining n-1 instruction, you will see that they will take only 1 cycle. For example, the instruction I2 is being completed in the 6th cycle. So if you see how many cycles are used by the instruction I2, only 1 cycle. Why? Because I2 instruction is already reusing the cycle number 2 3 4 5, right? So this is happening in the parallel. So these are not extra cycles. I2 instruction is using only 1 extra cycle, and you will see that I3 instruction is also executed in 1 cycle. That means in the 7th cycle the 3rd instruction is executed, then in the 8th cycle the 4th instruction will be executed, then in the 9th cycle the instruction number 5 will be executed. So like this it will keep happening. That means remaining n-1 instruction will take only 1 cycle. Remaining 1 instruction will take 1 cycle each. So every instruction will take only 1 cycle each, because in the 6th cycle, so I2 instruction is taking only 1 extra cycle, right? I3 is taking only one extra cycle. So from this you can say that the number of cycles taken by any pipelining system, if let us say you have n instructions in the processor, and there are k stages of the pipelining, then you can say the number of cycles required to execute n task on k stage pipelining, number of cycles in case of pipelining, right? Or you can say execution time of pipelining. So it will be, you can see that the first instruction will take k cycles and remaining n-1 instructions will take n-1 cycles. So the total number of cycles required to execute the n instruction in k stage pipelining will be k plus n-1 cycles. If let us say the cycle time is set to be TP, let us say cycle time of pipelining, then the execution time in seconds or nanoseconds or milliseconds will be k plus 1 n-1 into TP, that is the cycle time, right? So this will be the execution time in case of pipelining. And you will see that when you have enough number of instructions, the CPI of the pipelining will become 1. So you can observe here we have not completely filled the pipelining, right? So for example, if you will keep increasing the instructions, CPI will keep decreasing. So for example, here you can see that total it took 8 cycles to complete 4 instructions, right? You had 4 instructions, you have executed 4 instructions, and the 4 instructions are taking 8 cycles. That means the cycles per instruction here is CPI is 8 by 4, that is 2, right? CPI is 2 right now when we have only 4 instructions. When you keep increasing the instruction, for example, the 5th instruction will be executed in the 9th cycle, right? In the 9th cycle this instruction will also be finished. That means in the 9th cycle 5 instructions will be executed. Then in 6 instruction will be executed in the 10 cycles. Then 7 instruction will be executed in the 11th cycle. 8 instruction will be executed in the 12 cycles. So you can see here, as you are increasing the number of instruction, the CPI is decreasing. For example, in this case the CPI will become less than 2 because 9 by 5 is less than 2, right? And then if you will see this 10 by 6, then CPI will become, I think, 1.8, right? Something like this. Then this will be less than 1.8. Then 12 by 8 will be more less, that means it will be 1.45, something like this, right? So CPI will keep decreasing and the number of instructions will increase. That means in the ideal situation you can say that the CPI of the pipelining is 1 under the ideal condition. Ideal condition means that when you have many instructions, millions of instructions. Okay, so when you have millions of instructions, then CPI of the pipelining will become simply 1. So let us write it down. CPI of pipelining is always 1. Okay, that means the cycles per instruction, or you can say the number of cycles taken per instruction in case of pipelining will be always 1. Not always 1. Actually, when we have the stalls in the pipelining, or you can say we have the waiting cycle in the pipelining, then the CPI will actually increase, and we will see how that cycle will that will be increasing. Okay, so mainly when we design the pipelining, what we do is we will keep small buffers between the stages. So when we design the pipelining, we will have the buffers in between the stages. For example, let us say this is your instruction fetch stage. After the instruction fetch stage, you will be having a small buffer, which is also called as a small register, or we can say latch. So sometimes it is called as pipeline register, or sometimes it is called as latch, or simply a buffer. So the output of the instruction fetch stage will be available in this buffer, and then instruction decode stage will take the input from this particular buffer and will produce the output in the next buffer. Then the operand fetch stage will take the input from this particular buffer and will produce the output and will put into a buffer. Then next operation performed, or you can say execution stage, will take the input from this buffer and then will produce the output in one of the buffers, right? And then write back stage, which will be, so output of the instruction will be available out after the write back stage, right? So these buffers will be very useful. You will see in case of data forwarding, these buffers will be very useful. We will see how we will utilize these buffers in case of data forwarding or bypassing or operand forwarding, you whatever you can call them, right? So these are very high speed buffers which are connected between the stages. So the output of one stage will be available in the buffer, and the next stage will take the input from the previous buffer, right? So how, now the question is how we will connect all these stages to a single clock so that they are synchronized, right? So all these stages of the pipeline are connected to a single, you can say a same clock, and the output of one stage will be available at the end of the cycle. So this is your clock to which all the stages are connected, and the frequency of this clock will depend on the slowest unit of the pipeline. For example, let us say all the pipeline stages are taking the same amount of time. Let us say buffer takes 1 nanosecond, buffer delay is 1 nanosecond. Let us say this is 1 nanosecond. This is, all the stages are taking same amount of time, something like this. Okay, so in this case, when we talk about the frequency of this clock, the frequency of this clock will be set to the stage delay plus the buffer delay. That means if we talk about the cycle time of the pipeline, the cycle time of the pipeline will be maximum of all the delays in case of non-uniform pipeline. We will talk about what is non-uniform pipeline, but this is called as uniform delay pipeline. Uniform delay pipeline means that every stage is having the same delay, that is 10 nanosecond. So maximum of all the delays plus the buffer delay. For example, in this case, the maximum of all these will be 10 nanosecond plus buffer delay is 1 nanosecond. That means the cycle time of the pipelining system will be, or you can say pipelining processor will be 11 nanoseconds. So the frequency of this clock will become 1 upon 11 nanoseconds. Okay, so according to this answer will be in gigahertz. So remember, if the time is given, if the cycle time is given in nanosecond, then the frequency will be in gigahertz, or you can say if the frequency is given in gigahertz, then the cycle time will be in nanoseconds. You can convert also, but it is not mandatory. If it is given in microsecond, then the frequency will be in megahertz, and if the time is given in milliseconds, then the frequency will be in kilohertz, or simply if it is given in seconds, then it will be in hertz. Okay, so the clock frequency will be set according to the slowest unit of the pipeline, and it is also logical. You can think of the example in which you can take the example of the assembly line of a manufacturing unit. So you know that let us say there is a unit which is taking 2 hours to complete, and all the other units are taking 1 hour. So it makes sense to set the clock time according to the slowest unit of the pipelining, right? So you know that we have discussed this, that if you have n task to complete on the pipelining processor, then the first task, or you can say the first task will take k cycles, right, and k is the number of stages in the pipelining, right, and remaining n minus 1 task will take n minus 1 cycles, because after every cycle the output of the instruction will be available. That means after every cycle, after the k cycles, one instruction per cycle will be executed, right? The first instruction will take k cycles, but after that every instruction will take only one extra cycle. That means total number of cycles required in case of pipelining is will be k plus n minus 1 cycles, right? If the cycle time is given, you can multiply by cycle time. You will get into, so you will get the answer in seconds or nanoseconds, whatever. So for example, let us say you want to execute 1000 tasks on a pipeline processor with k equals to 5 stages. Okay, so how many cycles it will take to complete the execution? So number of cycles required will be k plus n minus 1, that is k is 5 plus 1000 minus 1, that is 1004 cycles will be required to complete these tasks on the pipelining system. And if you execute these tasks on the non-pipelining system, then it will take how many cycles? Each instruction will take 5 cycles. That means 1000 instruction will require 5000 cycles, right? If you talk about execution time in case of non-pipelining processor, in non-pipelining processor we know that task will be executed in sequentially, right? So first instruction will go through all the 5 cycles, then second instruction will go through all the 5 cycles, and so on, like all the 1000 instructions will go sequentially through 5 stages. So this means that it will take 5 cycles to execute each instruction in case of non-pipelining processor, right? So this means that the CPI of the non-pipelining processor is actually equal to number of stages, right? Or you can say that in this case the execution time of non-pipelining in number of cycles will be 5000 cycles, right? And from this you can also find out one more very important thing, that is called as speed up. So we will talk about what is speed up. It is because we are using the non-pipelining system and we are using pipelining system, so there must be a reason why we are using pipelining system, because the throughput of the pipelining system is very good, right? And what is throughput? Throughput is nothing but simply number of tasks executed in per unit time. So for example, let us say we have n tasks that we want to execute, right? And let us say we have a non-pipelining processor. We have a non-pipelining processor which takes let us say 5 cycles per instruction. Okay, we have a non-pipelining processor which takes 5 cycles per instruction in case of non-pipelining processor, right? And let us say if the n tasks are executed on the pipeline system, and in the pipeline let us say we have 5 stages. Then if we talk about in case of non-pipelining, execution time in case of non-pipelining will be the number of tasks into the time taken to execute one task in non-pipelining system. So this will be the execution time in case of non-pipelining system. And if we talk about the execution time in pipelining, execution time in pipelining will be simply k plus n minus 1 into cycle time in the pipelining system, right? So from this we can find out the speed up of the pipelining system over non-pipelining system. Speed up is nothing but the performance of the pipelining system, performance of pipeline divided by performance of non-pipeline. And the performance will always be the inversely proportional to the execution time. For example, if your execution time is more, then the performance is decreasing, right? If the performance is increasing, this means that execution time is less. So performance is inversely proportional to execution time, right? So we can say that in this case performance of the pipelining, let us say performance of the pipelining is one of the execution time in pipelining system, right? And performance of non-pipelining is, let us say, 1 upon execution time in non-pipelining system. So the speed up will become simply execution time in non-pipelining divided by execution time in pipelining system, right? So execution time in case of non-pipelining system is, let us say there are n tasks and the cycle time of the non-pipelining system is, let us say, tn, right? And let us say in case of execution time of pipelining will be k plus n minus 1 into TP. Let us say TP is the cycle time of the pipelining processor, and TN is the cycle time in the non-pipelining system, right? Or you can say the time taken to execute one task in case of non-pipelining. So this will be your speed up, that is n into Tn divided by k plus n minus 1 into TP, right? And in the ideal condition, if we assume that if what the ideal condition I'm saying that if the pipeline is perfectly balanced means that, for example, if let us say in the non-pipelining system, it takes to execute one task, it takes 40 nanoseconds. Okay, in the non-pipelining system it takes 40 nanoseconds to complete the task. So if let us say we have 4 stages in the pipelining system, and the delay of each stage is, let us say, 10 nanoseconds. In this case, we can say that the pipelining stages are perfectly balanced. Perfectly balanced means that the time taken in the non-pipelining system and the time taken in the pipelining system is actually simply, if we can, from this we can simply say that the time taken in the non-pipeline system is simply k into TP. Okay, in this case we say that the stages are perfectly balanced, and this is actually theoretical. The execution time in the pipelining system, or you can say the cycle time of the pipelining system, cannot be equal to the non-pipelining processor. The reason is that due to if we have the pipelining system, there will be some delays. For example, there will be some stage delays. We will have to adjust the clock frequency due to the slower units in the pipelining system, and there are many other issues. That means the cycle time of the pipelining system cannot be equal to non-pipelining system. But the researchers have tried doing this, but that is not possible, right? So we can say that under the ideal conditions, if let us say if you have the number of tasks, if the number of tasks increases, or you can say the value of n is very large, right? N becomes very large, then k minus 1, right? You know that the number of stages will be 4, 5 or 6, and if you have millions of instructions, then millions and k minus 1, you can say k minus 1 is simply, if you have k equals to 6, so k minus 1 will be 5. So 5 in comparison to million is actually a very small value, right? So what we can say that is, if we have, so this is called as ideal condition when you have very large number of instructions. In questions it will be, sometimes the number of instructions will not be given, they will simply ask you and under the ideal condition. That means under the ideal condition means that when we have very large number of instructions. So when we have very large number of instruction, n becomes very larger than k minus 1, so k minus 1 will not actually matter, so we can remove that from the formula. When the n is very large than k minus 1, for example, n is 10 to the power 9 and k minus 1 is only 5, so in the k plus n minus 1 formula, so for example, you can write it like this. So do not be confused between small letter and capital letter. You can write it like this, n plus k minus 1, right? So the same thing. So when n becomes very large, this value will not matter actually. So under the ideal condition, you can say that, so we know that speed up is number of tasks into time taken in non-pipelining system divided by k plus n minus 1 into cycle time in pipelining, right? So if we remove k minus 1, and the number of tasks are same in pipelining system and non-pipelining system, right? So this will become, this speed up will become under the ideal condition the time taken in non-pipelining system divided by, so k minus 1 can be removed when n becomes very large, so that this will not be significant. So this will become Tn divided by, so n into Tn, the n is number of tasks, divided by n into Tp. So we can cancel out number of tasks. That means under the ideal condition, the speed up is simply the cycle time in non-pipelining system and divided by the cycle time in the pipelining system. Or you can say that time taken to complete one task in non-pipelining system and time taken to complete one task in the pipelining system. And this is under ideal condition. That means when we have very large number of instructions. So sometimes in the question they will simply ask you, let us say in the pipelining system it takes 40 nanoseconds to complete a task, And in the pipelining system, we have 5 stages of the pipelining, in which the delay of the pipelining stages will be given, and they will ask you the speed up under the ideal condition. In that case, you can use this particular formula. So we will solve the question on each and every concept. Do not worry about this, but this is important. And this further can be extended if, let us say, I told you that when the stages are perfectly balanced means that every stage is taking the same time, and the clock frequency is also equal to the, so the frequency of the clock is equal to the pipelining, non-pipelining and pipelining is same. What I mean to say is that, let us say there are 5 stages. Let us say instruction fetch, instruction decode, and operand fetch, execution, and then let us say write back. These are the stages through which every instruction will go. Does not matter it is pipelining or non-pipelining system. Obviously in the non-pipelining also all these things happen, right? So in the, let us say we have a non-pipeline processor in which the cycle time is, let us say the cycle time is equal to 10 nanosecond, right? So every stage will be completed in one cycle. That is the first requirement. So all these stages will be connected to a common clock, and this clock will run according to the cycle time. Obviously cycle time depends on the clock frequency. So if the cycle time is 10 nanosecond, that means the frequency is 1 upon 10, or you can say 0.1 gigahertz, right? This is the frequency of the non-pipeline processor. So it will take 10 plus 10 plus 10 plus 10, that is, if for executing one task it will take 15 nanoseconds, right? In case of non-pipelining system, to complete one task it will take 15 nanoseconds, right? And if we have a pipeline processor, you know that the same clock, so what is the requirement here is that we are using the same clock, right? So these are the 5 stages of the pipelining system, and the same clock is there. That means the cycle time in this also 10 nanosecond, right? So you can say that the cycle time in case of pipelining is also 10 nanosecond. And you know that in case of pipelining, the CPI is 1. That means in one cycle one instruction is executed when we have a large number of instruction. So in this, one task is completing in the 15 nanoseconds, and in this one task is completing in one cycle, or you can say 10 nanoseconds. So in pipeline system it is taking 10 nanoseconds. In non-pipeline system it is taking 15 nanoseconds, because the clock is same. But that is actually not possible. That is only theoretical. When you convert a non-pipeline processor into the pipeline processor, there will be some delays. There will be some, for example, clock setup time. Okay, stage delays may be different, or for example we will be having the buffers between the stages. So the cycle time will actually increase, so that frequency will decrease. That means the cycle time cannot be same. But theoretically we can say, this is important point, theoretically it is not practically possible to achieve the maximum speed up. We are going to talk about the maximum speed up. Theoretically, when the Tn, that means the time taken in the non-pipelining processor, is equal to the number of stages into the cycle time in pipelining processor, that is Tn equals to k into Tp, where k is the number of stages, Tn is time taken to execute one task in non-pipelining, right? Time taken to execute one task in non-pipeline, and this is cycle time of the pipeline, or you can say the time taken to execute one task on pipelining system. So you can see here that in the non-pipelining system it is taking 15 nanoseconds, because we have 5 stages. So Tn is equal to 15 nanoseconds and Tp is equal to 10 nanoseconds. So that's how we are getting this particular formula. When the task executed in the non-pipelining system is equal to k into Tp. So in this case you will achieve the maximum speed up. Maximum speed up means that, so you can put this value Tn equals to k into Tp in this formula, right? Tn equals to k into Tp. So when Tn is equal to k into Tp and divide by Tp, right? So this will become equal to k. That means the maximum speed up achievable in pipelining is equal to the number of stages in the pipeline, right? Number of stages, that is the maximum speed up achievable in the pipelining processor. And this is only theoretical. That is till now the researchers have not reached this particular speed up, but we are close to this. right? Then you can find out the efficiency of the pipelining system by simply calculating the speed up and dividing by number of stages. So this efficiency is simply telling you that maximum speed up achievable is number of stages, and you are able to achieve this. For example, you can say that, let us say there are 5 stages. Okay, that means the maximum achievable speed up is 5, and you calculated the speed up equal to 2. That means non-pipelining processor is 2 times faster than the non-pipelining processor. Speed up is simply nothing but a factor by which the pipelining processor is faster than the non-pipelining processor. So in this case you are getting 0.4. that means the frequency, that is efficiency of your pipelining processor is 40%. Your pipeline processor is 40% efficient. So 40% efficient means that it could achieve, that means the maximal achievable speed is 5, but it is able to achieve only 2 speed up of 2. Or you can say, in the normal real life example, you can say that you have 24 hours. That means you can study for 24 hours, but you are able to study only for 12 hours. That means your efficiency is 50%. Obviously you cannot avoid the sleeping. Let us say 6 hours of sleep is enough if you are preparing for any exam. That means you have total 18 hours remaining. So maximum achievable efficiencies, so 100% efficiency is 18 hours when you are working for 18 hours. But let us say you are studying only 9 hours. So 9 by 18, that means your efficiency is 50%. You can work for 18 hours, but you are working only for 9 hours, or you are studying only for 9 hours. That means your efficiency is only 50%. So that is the efficiency of the processor, of the pipeline processor, right? So throughput, I do not need to tell you. Throughput is nothing but simply the number of tasks executed in per unit time. Or let us say you are able to execute five tasks. So you can write it. It will help you because there are 1 or 2 questions on the throughput as well in GATE computer science. So throughput is nothing but total number of tasks performed divided by total time taken to perform these tasks. Okay, let us say in the pipelining processor you executed 100 instructions in, let us say, 1000 nanoseconds. So the throughput is simply, you can say 1 upon 10, or you can say 0.1. That is 0.1 instruction is being executed per nanosecond, right? So there are typically many kind of pipelining, but mainly we are interested in only 2 type of pipelining processors. That is, first one is called as uniform delay pipeline. So uniform delay pipeline simply means that in this pipelining all the stages complete their task in the one cycle, or you can say in the same time or same cycle time, right? So let us say the clock cycle time is, let us say the cycle time of the processor is TP, right? So the time taken, or you can say the cycle time of the pipelining processor will be simply the cycle time given of the processor plus stage, or you can say the buffer delay if given in the question. Sometimes buffer delay will also be given. So the pipelining processor will be having the cycle time equal to the cycle time of the stage plus buffer delay, right? So TP plus latch delay, or you can say buffer delay. For example, let us say you have given a system in which you have 5 stages and each stage takes, let us say, 20 nanosecond. It will be given in the question like this: each stage takes 20 nanosecond. That means it is a uniform delay pipeline. And let us say the buffer delay, there are buffers between the stages and the buffer delay is, let us say, 2 nanoseconds. How much time it will take to execute, let us say, 100 tasks on this pipelining processor, right? So you will apply your formula, that is execution time in case of pipelining processor will be k plus n minus 1 cycles, and the cycle time will be TP. So TP you will have to calculate in case of uniform delay pipelining. In case of uniform delay pipelining, TP will be simply the cycle time given, that is 20 nanoseconds, plus the buffer delay, that means TP will be simply 22 nanoseconds, right? So execution time in case of pipelining will be 5 stages are there, 100 instructions are there, minus 1 into 22, or you can say 104 into 22, or you can say 2288 nanoseconds, right? Then second kind of pipelining is non-uniform delay pipelining. The non-uniform delay pipelining are simply the pipelining in which the stage delays are non-uniform, or you can say unequal. Non-uniform delay pipeline. In the non-uniform delay pipelining, you will be having the system something like this. Let us say this is your stage 1 and there is a buffer connected. Okay, then let us say the stage 2 in which the output of this particular stage is available in this buffer. Then there is a stage 3 which is taking the input from the buffer produced by the stage 2 and putting the result in another buffer. Let us say like this, you have 4 stages of the pipeline. Let us say the stage 1 takes 10 nanoseconds, it takes 2 nanoseconds in the buffer, and it takes 15 nanoseconds, and let us say it takes 12 nanoseconds in the stage 3, and in the stage 4 let us say it takes 14 nanoseconds, right? So in this case, what will be the cycle time of the pipeline processor? So the cycle time of the pipeline processor will depend on the slowest unit of the pipeline. Slowest unit means that the unit which is taking the most time. So maximum of stage delays plus latch delay, or you can say buffer delay. So in this case, the cycle time will be the maximum of 10, 15, 12 and 14 plus the still latch delay is 2 nanoseconds, right? So maximum of these is 15 plus 2 is equal to 17 nanoseconds. That will be the cycle time in case of non-uniform pipelining processor, right? Let us say you are given a question in which you have to execute, let us say 100 tasks, and there are 5 stages in the pipelining processor, and they takes, let us say 10, 20, 22, 18 and 19 nanoseconds respectively. Okay, stage 1 takes 10 nanoseconds and stage 5 takes 19 nanoseconds, and let us say there is a buffer between the stages which takes, let us say 3 nanoseconds. How much time it will take to execute 100 tasks in case of pipelining processor? So execution time in pipelining processor will be simply maximum of all these, that is first you will have to calculate the cycle time. So cycle time will be maximum of these 22 nanoseconds plus buffer delay, that is 3 nanoseconds, that will be 25 nanoseconds, right? Then you will apply your formula, that is k plus n minus 1 into TP, which will be simply the number of stages 5, number of instructions minus 1 into 25 nanoseconds, right? So 104 into 25. So whatever it will come out to be, that will be your answer. That is your non-uniform delay pipelining. So consider a question and try pause the video and try solving this question by yourself. Consider an instruction pipeline which has speed up factor equal to 10 and operating with 80% efficiency. Find out the number of stages in this pipelining processor. What will be the number of stages? So we know that the efficiency of the processor, of the pipeline processor, is simply speed up divided by the number of stages, right? The efficiency is given 0.8, or you can say 80%, and speed up is given 10, right? So number of stages you need to find out. So the number of stages will be 8, right? Sorry, not 8. So the number of stages will be k equal to 10 by 0.8, right? Or you can say 100 divided by 8. It will be 12 point something, which will be approximately 13 stages. So stages cannot be in fraction, so 13 stages will be required in this particular pipeline processor. Okay, so let us look at one more question. So these are the simple basics of the pipelining. We will move forward and we will look at the more complex topics, but this will simply build your basics of the pipelining, right? Let us say there are two pipelining processors, A and B, right? And let us say in A processor we have 8 stages, and it is a uniform delay pipeline. Uniform delay pipelining means that it is a uniform delay pipeline in which every stage is taking 2 nanoseconds. Okay, every stage is taking 2 nanoseconds. And we have a B in which number of stages are 5, and it is non-uniform delay. Non-uniform delay means it is taking every stage is taking different time. For example, the stage 1 is taking 2 nanoseconds, second is taking 3 nanoseconds, then 1 nanosecond, 2 nanosecond, and 2 nanosecond. So you need to find out, if we execute 100 instructions, on these processors, on these processor A and processor B, how much speed up will be achieved if we use A pipelining instead of B. So how much time processor A will be faster, or you can say the pipeline A will be faster than pipeline B. So if you do about A, in case of A, how much time it will take? K plus n minus 1 into TP, right? That is, number of stages are 8, number of instructions are 100, minus 1 into 2. And in this case it will take, so TP will be maximum of all these, that is 3. That means number of stages are 5, number of instructions are 100, and TP in this case will be 3 nanoseconds. So in this case it will take 104 into 3 nanoseconds, or you can say 312 nanoseconds. And it will take in this case 107 into 2, that is 240 nanoseconds. So you can see how much time will be saved. So how much time will be saved if we use A instead of B? 312 minus 240 nanosecond, that is 98 nanosecond will be saved, right? So these are the basic things about the pipelining system, and there will be many type of questions that we will see in the upcoming lectures. So for example, now we will move forward to our main topic, that is RISC pipelining. Okay, so the RISC instruction set contains 3 kind of instructions, that is data manipulation instruction, or you can say ALU instruction, in which you will play with the data, like your arithmetic instructions, logical instructions, right? Then load and store instructions, that will be used for moving the data. So RISC pipeline, or you can say the RISC processor, is also known as load store processor, because in this the memory will be accessed with only 2 instructions, that is load or store. If you want to bring something from memory to registers, you will use the load instruction, and if you want to store something from the register to the memory, then you will use the store instruction. So there are 3 categories of instructions in the RISC pipelining, that is ALU instructions, load and store, and branch and jump instruction. These are called as transfer of control instructions, right? And in the RISC pipelining we have the 5 stages. This is the important part to understand what are these 5 stages. The first stage is instruction fetch cycle, and in the instruction fetch cycle what you will do is you will fetch the instruction from the memory based on the program counter value, and in the same cycle you will increment the value of the program counter to simply to point to the next instruction, right? So it takes 5 clock cycles. That means there are 5 stages, right? Every stage takes 1 clock cycle, so it is implemented in 5 clock cycles. In the instruction decode or register fetch cycle, this is an important cycle of the, or you can say important stage of the pipelining. in which you are doing the two things, that is you are decoding the instruction. Decoding instruction means that you are trying to find out what kind of instruction it is. It is a data manipulation instruction or data transfer instruction, or it is a transfer of control instruction, that you are trying to find out with the help of decoding the instruction. And in the same cycle, what you are doing is you are fetching the registers, register fetch cycle. Sometimes it is also called as register read cycle. Instead of instruction decode, it is also called as register read cycle, RD cycle. In this cycle, what you do is you will fetch the, if the source operands are registers, you will fetch the source registers. For example, let us say we have the instruction like this: add R1, R2, R3. In this, what you are doing is you are adding the value of R2 and R3 and writing the result into the register R1. So these are the two register operands. That means these two register operands will be read in the same cycle. So these two things will happen in the parallel. That means decoding the instruction and reading the registers for the input operands. So these two things are done in the same cycle. That means in the second cycle, you are fetching the operands from the registers. And remember this: if one of the operands are in memory, this will not be done in this cycle. So in this cycle, you are only fetch the operands which are available in the registers, right? You will not access the memory in this cycle. For accessing the memory, we have a different cycle. So the third cycle will be execution or effective address calculation. So execution means, if let us say you have the ALU instruction, so addition, subtraction, multiplication, or increment, decrement, that will be done in this cycle. Or if you have a load or store instruction, in that case the effective address will be calculated in this cycle. That means two things will happen in this third cycle: performing the operation if it is a ALU instruction, and if calculating the effective address if it is a load store instruction or it is a branch instruction. Calculating the effective address simply means that if let us say you have instruction something like this: load 20 R1, and let us say in the register R1 you have some address 1000. Calculating the effective address means that simply you are trying to calculate from where we need to load the operand. So effective address, as we have studied in the addressing modes, effective address in this case will be 20 plus R1, that is 1000. That means the effective address is 1020. So this effective address will be calculated in this particular cycle if it is a load or store instruction. But we will not read the memory, we will not access the memory in this cycle. We are only calculating the effective address if it is a load or store instruction or it is a branch instruction. But if it is a simple ALU instruction, then execution will be done of the ALU instruction. And in the ALU instruction, we may reference the memory. For example, one of the operand is available in the register and one operand is available in the memory. In that case, you will have to reference the memory. And it may be register to register ALU instruction like add R1, R2, or it may be register immediate. That means you are adding an immediate value, or you can say you are adding a constant value with the register value. So all these things will be done in this cycle, in the execution cycle, right? So this is a very important point. In the second cycle, you are decoding the instruction and parallelly you are fetching the values from the register. That means you are reading the registers. And in the third cycle, you are executing, or you can say you are performing the ALU operations, or you are calculating the effective address for the load or store instruction, from where you need to load the value or where you need to store the value, right? So fourth cycle is memory access, and this cycle will not be applicable to all the instructions. For example, let us say you have instruction something like this: add R1, R2, R3. In this particular instruction, you do not need to access the memory, right? So there will be some memory based instruction in which you will access the memory, but in all the instructions you will not access the memory. So memory access will be done in this particular cycle. For example, in this particular cycle, you have calculated the effective address. That means from where in the memory you need to load the value. For example, let us say this is your main memory, and in this, on the address 1020, you have some operand. So this operand will be loaded into the accumulator in this cycle, memory access. That means read or write will be done in the fourth cycle, right? If the, or you can say if the destination operand is the memory address, then that will be done in the memory access cycle. Now the last cycle is write back cycle, and this is very important. In the write back cycle, what you are doing is you are writing the result into the destination register. Remember, in the write back cycle, you are not writing the operand into the memory. you are writing into the registers only. For example, if you have like this, add R1, R2, R3, and the interpretation of this instruction is, let us say, R1 to R2 plus R3. So these two registers will be accessed, that means input registers, or you can say the input operand from where we need to add the values, will be accessed in the instruction decode or register read cycle. And the result, so then you will add those two values in the execution cycle, right? In the execution cycle you will perform this operation, ALU operation. Then in the fourth cycle we do not need to do anything, because we are not having any memory operand here. In the last cycle you will write the result into the register R1. That means in the write back cycle you are writing the result into R1, right? And you will see that we will be using the split phase technique. Split phase technique means that when you have a cycle, this same cycle can be divided into two parts, and in the first half of the cycle you can perform register read operation. In the second half of the cycle you can perform write back, or maybe opposite. In the first half of the cycle you can write back the result into the registers, and the next instruction can read from this in the same cycle, right? In the split phase technique, what we do is the same cycle is divided into two parts. What we are saying is that in the rising on the rising edge, what we'll do is we'll write into the register, and in the falling edge we will simply read from the register. So in the same cycle you are writing and reading. So these two tasks can be done in the same cycle. That is an optimization for the pipelining. So the main thing is to understand what is happening in these 5 cycles. So in the first cycle you are fetching the instruction from memory and updating the program counter value for the next instruction. In the instruction decode or register phase cycle, in this you are decoding the instruction, and in parallel you are fetching the source operands from the registers if they are the register operands. In third cycle you are performing the operations, or you are calculating the effective address for the load or restore instructions, or for the branch instruction. If you are branching to some random address, the target address will also be calculated in this particular cycle. In the fourth cycle you are accessing the memory. That means if it is a branch or load or restore instruction, the effective address is calculated in this particular cycle, and from that address you will access the memory in this cycle. Then the result will be written back to the write back stage in the fifth cycle. The interpretation of these cycles is something like this. So you will access the memory, and that location will be pointed by program counter. So this is in the short, right? We have seen the complete set of micro operations for the instruction fetch. For example, initially you will move the value from program counter to MAR, that will be the address. Then you will read the memory from MAR and you will transfer the instruction into MDR, right? And in the same cycle you can increment the value program counter, and then you will simply transfer the instruction from MDR to instruction register, right? So this is the short form of these 4 micro operations. The main thing is that in this we are fetching the instruction on the basis of program counter value into the instruction register, and then you are incrementing the program counter to new program counter value, right? And then in the instruction decode or fetch register fetch cycle, what we are doing is we are fetching the source registers into the temporary registers A and B, and if there is an immediate value, that immediate value will also be loaded, and then the in the next cycle execution will be performed, right? So decoding and register read is done in parallel. This is very important point. So execution or effective address calculation, for example, if we have the ALU operation between some register and immediate value, then this operation will be done in this particular cycle, and the output will be available on the ALU output cycle, right? So like this, all these operations, addition or A func B, or all these operations, so whatever operator is there, that operator will be performed in this cycle. And if it is a branch instruction, you will check the branch and will calculate the effective address, or you can say will calculate the target address. So normally the target address of the branch instructions are available in the instruction decode cycle, but in the question it will be always given that when the branch is being calculated, that means when the target address is available or branch is evaluated. So when the branch is evaluated, in which cycle the branch is evaluated, according to that the number of stall cycle will be there. But that is a very far topic, but for now we need to understand what is happening in all these 5 cycles, so that you can understand better what will be happening in this cycle. For example, let us say these are the 5 instructions we are executing in the pipelining. These are the clock cycles. So in the first clock cycle you will fetch the instruction I, then you will decode it, and in the second cycle the fetch unit is free, so we can start fetching the next instruction. Then the instruction 1 will go into the execution stage, then the second instruction will go in decode, and third instruction will go into the fetch stage. So like this we have the overlapping stage. For example, in the 5th cycle there are 4 or 5 operations are happening. You are writing back the result of the instruction I, you are accessing the memory for the instruction 2, you are executing the instruction 3, you are decoding the instruction number 4, and you are fetching the instruction number 5. That means in 9 cycles you have executed 5 instructions. And remember that 2 stages cannot overlap in the same cycle. How practically it is being done? So if we look at the hardware that will be used by each cycle, so assuming that we have the different memory for operands and instructions, so you know that a program is simply set of instruction and data. So if you keep the instruction and data in the same memory, there may be some issues. We will see what can be that issue. So that may cause the structural hazard, right? That we will see how. But for now we are assuming that the instructions are available in the instruction memory, that is IM is the instruction memory, and data is available in the data memory. That means operands are available in the data memory. In the clock cycle 1 you will use the instruction memory to fetch the instruction, right? Instruction will be fetched from the instruction memory. In the second cycle you will decode the instruction, and parallelly you will access the registers, right? So in this, decoder will be used and the registers will be used. So you will access the registers and then you will perform the ALU operation, right? After performing the ALU operations, if let us say you need to write the result into memory, then data memory will be accessed. Otherwise, if the destination operand is the register, then directly we will send the output to the registers, right? So you can see there is a path directly without going into the direct memory, data memory. So this is due to if you have the instruction that is using destination as the register, for example like this. So in this case you do not need to access the data memory because we do not need to write the result into the memory. In that case, the ALU output can directly be sent to the registers in which we will write the result. Or if we have the instruction something like this, that means on the location number 100 we want to store the result of R1 R3. So in this case we will have to access the data memory and the address will be calculated in this particular stage, and finally the result of R1 plus R3 will be stored in the data memory. Then you do not need to access the register in the 5th cycle. So in the second cycle you will see that the instruction memory is completely free, it is not doing any task, so we can start fetching and we can use the instruction memory, and then we can overlap all the operations like this, right? Then in the third cycle instruction memory is free, so we can start fetching the third instruction. So these are the actually components that are used for each of these stages. For instruction fetch we use the instruction memory, for a register read we use the registers, for execution and effective address calculation we use the ALU, and for accessing the operands we use the data memory, and for storing the result we use the registers. So the results will be stored in the registers, right? Now there may be some issue. For example, if let us say we have the single memory for instruction and data, let's say we have simple memory, not instruction memory or data memory, there is only simple memory. So you will see that in the 4th cycle the instruction number I1 and instruction number I4, okay, let us say this is your instruction I1, this is I2, this is I3, and this is I4. In the 4th cycle we are accessing the memory for data for the instruction I1, and instruction I4 is also trying to access memory for the instruction. That means instruction I4 is trying to fetch and I1 is trying to read the operand from the memory. So in the same cycle we are accessing the same resource. This may cause a structural hazard, that is you can say resource hazard, in which there is a resource conflict. Resource conflict means that when we are trying to perform a operation on the same unit in the same cycle, right? This may be an issue. Now so that each of these stages does not interfere with each other, what we do is we will introduce a register between the stages, something like this. So, okay, there will be a very good benefit of these delays, these registers, or you can say buffers between the stages. So when you will fetch the instruction from the instruction memory, you will put it into this particular buffer. Then you will take the instruction from this buffer and you will start decoding it in the second cycle. Then you will access the operands from the registers and will put into the buffer. Okay, then ALU will take the values from the buffer and will perform the operation, and output ALU will put the output into this buffer. Then data memory will be taken, data memory will store this into the memory or registers, whatever, right? So these buffers are used so that the stages does not interfere with each other. And in the second, you will see that in case of data forwarding, what we can do is, if let us say there are two instructions which are dependent on each other, what I mean to say is, let us say we have the instruction something like this, and then there is an instruction, let us say R4 R1 plus R5. So you can see that the instruction I1 is writing into the register R1 and I2 is using this as an input. That means until R1 is not updated, you cannot use this as an input. If you use R1 before the R1 is being updated with the new value, then this instruction will read the old value, right? So this means that when finally the write back stage of the I1 instruction is completed, then only you can perform the instruction decode stage. Until that you will have to wait. But with the help of data forwarding, what you can do is, because after the ALU operation between R2 and R3, the result of R2 plus R3 will be available in this buffer, right? You do not need to wait till there. You can directly send the result from this buffer to the ALU of the next instruction, right? Like this, so that the input to the ALU will be feed forwarded, will go back into the ALU, right? So the benefit of this will be that the output of this instruction will be connected to the input of the next instruction, right? Because this requires, so this ALU requires two operands. The ALU of the second instruction requires R1 and R5. So R1 we require updated, so updated R1 is available here. So if we perform this instruction decode before the ALU operation of the I1 instruction, then it will fetch the old values of the R1, right? But with data forwarding, we can directly connect the output of one stage to the input of the another stage, right? That means we do not need to wait until the clock cycle number 5. In the clocks after at the end of the clock cycle number 3, the updated value for R2 and R3 will be available. That is so R1 is being updated with R2 and R3, R2 plus R3, and R2 plus R3 result will be available in this buffer when this instruction is completed. So these buffers are having very important functionalities. Now in the pipelining, we will be having some issues, and the issues in the pipelining are, for example, if you are having only one instruction to execute, the pipelining processor will actually increase the delay. It will not decrease the execution time of single instruction. As you know that the cycle, the frequency of the pipelining clock will be actually less than the less than your frequency of the non-pipelining processor, because in that we do not have any extra delays, right? So for example, if we have a non-pipelining processor, in this we have a clock which is running with the frequency of 4 GHz, and let us say the same clock is being, due to the clock skew time or clock setup delay time, clock setup or skew, or we can say due to the buffer delays, the frequency of the pipelining processor becomes, let us say, 3 GHz. So if you execute one instruction on the non-pipelining processor, it will be executed in, let us say, because cycle time will be 1/4, so it will be executed in 0.25 nanoseconds, one instruction in non-pipelining processor, and this will be 1/3, this means 0.33. So in case of pipelining processor, one instruction will be executed in 33 nanoseconds, and in the non-pipelining processor it will be executed in 0.25 nanoseconds. That means for a single instruction, the time taken, let us say the time taken in pipelining processor is T1 and the time taken in non-pipelining processor is T2. So the T1 will be always greater than equal to T2. That means the pipelining processor will not decrease the execution time for a single instruction, but because in the practical scenarios we are talking about lots of instruction, and finally we only interested in the throughput, so throughput will be best in the pipelining processor, right? So pipeline increase the CPU instruction throughput, the number of instructions completed per unit time, but it does not reduce the execution time of an individual instruction. That is important point. In fact, it usually slightly increases the execution time of each instruction due to the overhead in the control of the pipeline, right? Due to you will have to you will have to adjust the clock according to the slowest unit of the pipeline, right? So for example, look at this particular example. You will understand how the pipelining processor may become slower. Assume that a non-pipeline processor has 1 nanosecond clock cycle and that it uses 4 cycles for ALU operations and branches and 5 cycles for memory operations. Assume that the relative frequencies of these operations are 40%, 20% and 40% respectively. Suppose that due to the clock skew or setup, the processor adds 0.2 nanosecond of the overhead to the clock. That means if you talk about the cycle time in non-pipelining processor, okay, we have a non-pipeline processor. In non-pipeline processor, the cycle time is 1 nanosecond, right? And in case of pipelining processor, the clock will become little bit slower due to the skew and setup, and it introduces 0.2 nanosecond extra to the clock. That means the clock cycle time becomes 1.2 nanoseconds in the pipelining processor. So we want to find out the speed up of the pipelining over the non-pipelining processor, and it is taking that it is saying that it takes 5 cycles for the ALU operations and branches, and we have 40% and 40% instructions are ALU operations and 20% are branches and 40% are memory operations. So we have, you can say 40% operations are ALU operations, and ALU operations takes 5 cycles, right? And then you have 20% branch instructions which also takes 5 cycles. Then you have, okay, they use the 4 cycles. So ALU operations and branch instructions take 4 cycles to execute. We are talking about in the non-pipelining processor, right? And then we have the 40% of the instructions are memory instructions which take 5 cycles. That means the total time taken in case of non-pipelining processor will be 1.6 plus 0.8 plus 2.0, or you can say 3, so 4.4 nanoseconds will be taken in case of non-pipelining processor. And you know that in case of pipelining, the CPI is 1. That means it takes only 1 cycle to execute per instruction, right? CPI is 1 in case of in case of pipelining processor, and the cycle time is 0.2 nanosecond. That means it will take 1.02 nanoseconds in case of pipelining system, right? When the number of instructions are not given, you know how to calculate the speed up. So speed up will be execution time in non-pipelining processor divided by execution time in pipelining processor, and that will be 4.4 nanoseconds divided by 1.02 nanoseconds. Sorry, 1.2 nanoseconds. Okay, so this will come out around 3.67 speed up. That means your pipelining processor in this case will be 3.67 faster than the non-pipelining processor. Okay, so when we talk about the major problems in the pipelining, there are some things due to which there will be some issues, or you can say that the performance of the pipelining processor will actually decrease, or you can say degrade. So what are those things that can degrade the performance of the pipelining processors? So this will be discussed in the next lecture. Thank you, and next video will also be uploaded very soon after this video. So watch that video to know about the pipelining hazards and how to control them. So in the next class we will discuss all the hazards and the type of hazards and the solutions, how to overcome those hazards. And then in the third class we will discuss the previous year questions of the pipelining of GATE computer science. That means pipelining will be finished in 3 classes, and whatever I am discussing in the classes and through the questions, that will be more than enough to solve any question of the gate. Okay, so let's meet in the next class.